Yo, what's up everyone? Patrick here. Welcome back. Moving on to the next example. This one's going to be pretty intense, pretty complex as a heads up. So we got this piecewise function over here. So notice it has three pieces, right? This piece when x is less than 2, this piece when x is equal to 2, and then this piece when x is greater than 2. Notice that there's two unknowns as well, this a and this b that we're dealing with. So given this piecewise function here, we got to answer these two questions. Right, so we got to find the limit as x approaches 2 from the negative side of the function and from the positive side. And then for number 2, we got to find a and b, so this function is continuous at that x value of 2. So I'm actually going to erase this for now, give myself some room here. And so let's work with these two limits separately. So let's first start off with the limit as x approaches 2 from the negative side of this whole function, this whole piecewise function. Now, if we're approaching 2 from the negative side, which of these functions are we going to be dealing with? Well, we're going to be dealing with this function because this whole piecewise function is defined by this function when x is less than 2. And if we're approaching 2 from the negative side, then we're going to be approaching it on this function, on this piece over here. So this expression, we can actually rewrite as the limit as x approaches 2 from the negative side of that function on the left side. 2 sine x minus 2 over x squared plus x minus 6. Right? So this here, hopefully you realize at this point, this is a trig limit that we're dealing with. And I've done similar examples in the lecture videos. If you're not too comfortable with trig limits, highly recommend you go to the lecture videos and watch all those examples. I have a bunch there. But basically what we got to do here is first we got to factor that denominator. So that denominator is going to factor to x plus 3 and then x minus 2. And then notice that we have this x minus 2 and x minus 2 here. Now, in general, if you remember, we know that the limit as theta approaches 0 of sine theta over theta, that's just a fundamental trig limit. We know that that is equal to 1. Right? And it doesn't matter if we approach 0 or if we approach 0 from the positive side or if we approach it from the negative side. This limit here, it's always going to be 1. And so what we can do here is we can actually split up this limit into two expressions. So I'm going to say the limit as x approaches 2 from the negative side of, I'm going to take this 2, put it over the x plus 3. So that's going to be one limit. And then I'm going to have the limit as x approaches 2 from the negative side of sine of x minus 2 over x minus 2. Like that. Okay, and now notice that because I did that, this here is corresponding to this format. We can do a change of variable on this limit. Like if I take this limit and I work with it separately, I can say theta equals x minus 2. And so notice as x is approaching 2 from the negative side, the theta is going to be approaching 0. Right, so we can do a whole change there. So the limit as theta approaches 0 of sine theta over theta, we know that that's just going to equal 1. So this whole bracket is going to be 1. And if you actually wanted to make this a little bit more proper, if we're approaching 2 from the negative side, then theta is going to approach 0 from the negative side as well. Because like 1.99, for example, 1.99 minus 2 is going to be a negative number. So we're approaching 0 but from the negative side, so technically that should have been a negative there. But whichever way, either way, you should recognize that this here, right, this bracket, that limit, is going to be approaching 1. And so if that's approaching 1, if we continue this up here, we would end up having the limit as x approaches 2 from the negative side. Let's rewrite this limit here, 2 over x plus 3 times 1. We know this limit is approaching 1. And so for this one's pretty easy because notice that this function is continuous at 2 over x plus 3. so we could just do a direct substitution there. Right? So if we plug in 2 for x, this would end up being 2 over 5 times 1, 2 over 5 is the answer. Okay, so this limit here with all this work here is equal to 2 over 5. Right, so this limit is 2 over 5. Let me just circle that. All right, we're actually going to have to use this in number 2. Okay, so now what about this limit? The limit as x approaches 2 from the positive side of this whole function. Remember, f of x is this whole piecewise function. Now, if we're approaching 2 from the positive side, notice that this function is defined by this function when x is greater than 2. So if we're approaching 2 from the positive side, right, all of these values, all of these y values here are going to be defined by this function. And so what we can do is we can actually take this and rewrite it, the limit as x approaches 2 from the positive side of this whole function, x minus the square root of x plus 2 over b bracket x minus 2. This one's going to be a little bit more annoying because we got to deal with this b, but it's actually not bad. It's just a constant. If anything, you could actually factor it out too. Like you could write 1 over b and then rewrite this limit with just the x values. I'm just going to keep it there. It's not a big deal to deal with, but that is a constant, and so that's going to be part of this limit expression here. Now notice that we can't do a direct substitution. If I plug in 2 for x, denominator is 0. If I plug in 2 up here, 2 plus 2 is 4, square root of 4 is 2, 2 minus 2 is 0. So it's going to be in that indeterminate form. So we got to go about this a different way. What we can do is we can rationalize this. Notice we could rationalize the numerator, but we got to multiply the denominator by that same expression. Okay, so what we would end up with, I'm going to continue it here, is the limit as x approaches 2 from the positive side. We're taking this, multiplying it by the conjugate, so we just have to multiply the ends. So we would have x squared minus x plus 2 all over b x minus 2, and then I'm going to keep this expression separate. Like that. Okay, so from here, what we can do, distribute the negative inside the bracket. So this would actually turn into x squared minus x minus 2. This could maybe be your next expression here. I'm just going to sort of work with this numerator just to save space on the whiteboard. But you can just keep writing the same expression. So after distributing, we end up with this. And then notice that this can factor, right? X squared minus x minus 2 can factor into x minus 2, x plus 1, like that. And now what we can do, notice that those would cancel out. And now that those canceled out, we can actually do a direct substitution now. So we could plug in this 2 for this x value, we would end up with 3. And then if I plug in 2 here, 2 plus 2, 4, root 4, 2, plus 2, 4. So we would end up with a 4b, right? This b is still there in the denominator. And so this limit ends up being 3 over 4b. That is the answer for this part. That is the expression. And so now moving on to number 2, remember what do we got to do? We got to find this a and b. So this function is continuous at an x value of 2. And if you remember the fundamentals of continuity, what does that mean? If a function is continuous at a certain x value, in this case 2, what that means is that the limit as x approaches 2 from the negative side of the function has to equal the limit as x approaches 2 from the positive side of the function. And both of those have to equal the value of the function at that same x value of 2. Right? And so notice that we actually have expressions for everything. So we know this is equal to 2 over 5. We know this is equal to 3 over 4b. And we actually know what f of 2 is as well, because notice that this function at an x value of 2, that's the corresponding y value, a plus b, right? This is just a single point because it's only defined at a single x value. So this function actually has a point 2 and a plus b, like that. So this has to equal that, which has to equal a plus b. And then from here, you can actually make different, remember we got two unknowns here, so we need two equations. Well, we can make certain equations. We can maybe make these two equal. So let's say we let 2 over 5 equal 3 over 4b. And then from here, actually, we could solve for the b. And then we can also either make this equal to that or this equal to that. I'm going to let the 2 over 5 equal to a plus b. Right? We won't have to sub in another b. But you can also do this equals that. You're going to end up getting the same answer. No matter what answer I get, no matter which way you do this, you should get the same answer. So from here, let's solve for this b. We just cross multiply. 4b times 2 is 8b. 15 times 3 is 15, or 5 times 3 rather is 15. So b is equal to 15 over 8. So we know that for sure. And then we could plug in 15 over 8 for this b. Yeah, let's do that. I was going to multiply this by 5 to get rid of this denominator, but let's just work with fractions, whatever. Like that. And now we could solve for that a value. So the a value is basically going to be 2 over 5 minus 15 over 8. We got to get a common denominator, which is going to be 40. So we would have 16 over 40 minus 75 over 40. That's going to be a. And so when you do that, a would end up being, what, negative 59 over 40. And so those are the answers to this question, right? So the a and the b have to be these corresponding values, negative 59 over 40 and 15 over 8 respectively, in order for this function here to be continuous. All right, so pretty intense example. Lots going on here. We're dealing with a piecewise function. We're dealing with continuity. We're dealing with trig limits. We're dealing with limits with rationalization, right? So a lot of different concepts mix into one question. So we first have to find these two expressions, and then we know for the function to be continuous, this has to hold. And then if this has to equal that, which has to equal that, we can create two equations and then solve for that a and